Hey everyone, good evening, guys. Good evening, everyone. Awesome. So, what all we have done? We were at classification algorithms, right? Mm-hmm. So, we stopped that here, and we need to cover the random forest. Yeah, sure. We will be starting the random forest. That is the ensemble learning today. And yeah, that's it. That's what we need to do. Okay. Yes, please. Let me know if there are any questions, anyone. We can fill categorical missing values by mod in for loop, but can we do same for the integer and float type column by using the for loop? Yes, we can definitely do it. We can definitely use the for loop and loop all the columns to fill everything with mean or median, whatever we want to use. Like ideally, if we do so, we prefer mean, or we can use median also. Any such central tendency. That way, we cannot do the grouped mean method. We cannot do the grouped mean method, because in grouped mean we need to create separate function for every specific variable. So we can't actually do the grouped mean method, but we can, like, if we want to fill all the missing values with the mean, we can do. Yes, yes, that is we can do. That is something we can do. We can also write a if condition inside a loop, and we check if the instance of the column is integer or float, use mean, otherwise use mod. That is also something we can do, right? Yes, you can simply write a if condition inside, just iterate all the variables, all the columns, right? And iterate all the columns, check the instance of every column, what exactly is the data type, and based on that, just pick median or mod, whatever is required. Okay. Not yet, we haven't started anything. We are going to start now. And what we will be starting today is ensemble learning. Since last slide, you left your laptop in same condition. Since last few months, I'm doing this. Okay. So when it comes to ensemble learning, we have two types of methods: bagging and boosting. Bagging and boosting. We haven't started anything. It's just the heading. We have not discussed any concept yet. We just have the heading now. Ensemble learning. Let me just tell you the what exactly is this ensemble learning? Ensemble learning means by definition wise, when we combine weak learners to create a strong learner is called ensemble learning. Now, what is a learner here? Any algorithm that learns over the data, right? What all algorithms we have discussed, they all are learners, right? So, when we combine different weak learners to get a strong learner, that's called ensemble learning, right? Yes, guys? Means when we try to combine multiple algorithms to get more better results, strong results, that's called, that is what ensemble learning is called. Okay? A single algorithm is not giving accuracy? No worries. Let's combine multiple algorithms and let's see whether we are getting a good accuracy or not. Yes, using multiple models as a single model is what we refer as a ensemble learning. Perfect. Clear everyone? Okay. Now bagging and boosting. The name themselves are explaining what exactly we are trying to do. Bagging. We will see how does that works. We'll discuss about bagging and boosting, and we will see how exactly it's going to work. Okay. Let's let's discuss about the algorithms, the methods, the ways, and then we will get to know how exactly they are going to work. Okay. Perfect, guys. So the bagging and the boosting, two methods to apply the ensemble learning. Now, one by one, what do we understand by bagging? Bagging means simple bagging up something. For example, we have a data set, we have a huge amount of data, right? And we divided that huge amount of data into different subsamples, right? Random subsamples. Let's say we have 1000 observations or we have 10,000 observations. We created 50 random samples out of them. Possible? Yes. And we created 50 different decision trees for every sample. Again possible? Again possible? Okay, so the ensemble learning is like, suppose we want to attempt some exam and we like a single student, like if I want to attempt some exam or some certification, alone I can't cover all the syllabus. So what I'll do, I will, I will try to make a group of more people like me who are actually willing to qualify that exam or some certification. That's not practically possible, but let's take this example to understand what is ensemble learning. I'll try to collect some more people like me and I'll divide the entire syllabus. There are 50 chapters. I'll like, let's say we are 10 people. I'll say, okay, these 10 chapters you will cover, these 10 chapters you will cover, these 10 I'll take care of it, and that's how we divided the syllabus. And now we are all learned, right? We will learn on 10 chapters each. At the end, if we get somehow we get the chance that we can discuss and we can solve the solution, definitely we are going to get some better scores instead of learning all the 50 chapters alone, right? That is the concept of bagging. That is the concept of bagging. Yes, that is the concept of bagging. We have a huge amount of data and we divide that data into different small subsamples and we create different models on those subsamples. One of the possible bagging algorithm is random forest, right? So we know decision trees, and now there is a random forest. What is random? What is a forest? Group of lots of trees. A forest has a lot of trees. Yes. Yes. So this random forest is also going to have lot of decision trees. And why it's random? Because the data we are giving to those decision trees are completely random. We do not have some specific way of or specific criteria of dividing the data. So it's gonna be completely random. Right? So we divided the data completely random. We distributed that data to the different decision trees and they are learning. And that's how we have an entire forest. And now when a single new observation came in, every decision tree in the forest is giving the predictions. And the final prediction will be mod of all the predictions, right? Make sense? How random forest works? We have the data. Okay. Now we divided this data into lots of subsamples. Right? And on every subsample, we are building a decision tree. Decision tree 2. Decision tree 3. And so on. Decision tree n. Okay? Now they have different samples of data, so definitely their splits are going to be different. Yes, guys, every decision tree is taking different samples, so their splits are going to be different, right? And when there will be some new data, unseen data, right? Let's say there is only one observation, so every tree will make some prediction. Every tree will make some predictions, right? And we will pick the mod of all the predictions as a final prediction. So is it similar to grid search CV? Grid search, not exactly, because grid search is actually trying to go with the possible permutations and the combinations on a given parameters, right? Grid search is actually applying the permutation and the combinations on all possible parameters, and that's how it will retrain the model again and again on the entire data set. Grid search will not divide it. It will just give the entire data set for every fit. But right now what we are doing, we are dividing the data set into small subsamples and then we are training different decision trees, right? Got it? Yes, guys, got the concept of random forest? Easy? Easy? Everyone? Awesome. Awesome. Yes, the collection of decision trees. The collection of decision trees. After dividing, it's same as decision tree. Yeah, it's same as decision tree. How the decision tree goes? Similarly, every single decision tree will be trained on a that given subsample of data. Right? Awesome. 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 Perfect. Bagging is clear, everyone? Bagging is clear? It was easy. Now, the more interesting thing about ensemble learning is boosting. Right? Okay, so by the name itself, boosting, what do we understand? Yes? Powering up, increase, yes, powering up. We must have seen Sachin Tendulkar advertising about boost is the secret of my energy. So we are going to do something like that. We are going to boost up the accuracy, right? Yes, yes. Ensemble learning is the secret of our accuracy. Let's see how it can be secret of our accuracies. Okay, now the same example. The same example, there are 50 chapters we need to study for a single exam, and I can't cover all the 50 chapters. Now, what I'll do, I will not divide the random chapters to five people. What I'll do, I'll try, I have a given time frame. Let's say, um, I have my own limitations. Let's keep the time frame aside. I have some limitations, what I can cover, what I am capable of. So what I'll do, I'll try to attempt all the 50 chapters first. Okay, this is actually a sequential process. This is not a random. It's not a parallel process like bagging. It's a quite sequential process. So I'll try to cover all the 50 chapter once. Okay, first I started and I tried to learn all the 50 chapters. Once I am done, I will get to know that yes, I am confident in some of them, but again, I am not very much confident in some of them. Right? Possible? Yes, I tried to learn 50 chapters, but at the end of that entire learning, there could be a possibility that yes, I am confident on some chapters. Okay, I am very confident on these chapters. I can make good scores, but these are some chapters where I'm not very much confident. Possible? That's what usually we used to do, right? That's also a very practical approach. The person who is going to sit just next to us in the exam, we used to discuss this thing. Okay, so I have covered algebra, you will cover the probability, and we'll rock, right? That's how also we used to trick somehow. So here also, will this decrease the learning time by model? Since the data is splitted like distributed computing and bagging, no, data is distributed. Data is actually being you're talking about bagging right now, not boosting, right? You're talking about bagging right now. Yes? We'll talk about that. We'll talk about that. So there are different things. Actually, this has a completely different approach to reduce the execution time, right? It's not just by making the data samples, that there is something else to reduce the execution time. Apart from that, it's not going to reduce the execution time. Data is being divided, but again there are multiple models being built, right? Data is being divided, but there are multiple models that are being trained. Yes. So overall cost, if we talk about the computational complexity and the time complexity, is going to be exactly same. It won't reduce the computation or the time anything. It's going to be exactly same. How we can improve that, we'll talk about that. Okay. Okay. So where were we? About the boosting concept. Now okay, yes, I attempted some questions. I attempt a few, all the 50 chapters, but at the end of my learning, I got to know that I am confident in some of the lessons, but again, I am not very much confident on some of the lessons, like some other lessons in which I'm not very confident on, right? So what I'll do, I'll pass on this information to the next person that, okay, I have studied all the 50 chapters. You will also study all the 50, but please take some special care of these specific chapters, because I was not able to take or I was not able to understand much on them. Possible? Yes. I studied all the 50 chapters, but at the end of the entire study, I'm confident in some of them, but I'm still not very much confident in few of them. So I'll pass on this information to the next person. So he will also he'll study all the 50. Like it won't, he will be only studying those specific ones. He will also study all the 50, but he will give some more attention to the one in which I'm not confident. Right? Make sense? Yes, guys? Now that second person is going to have its own weaknesses. The second person, he also tried to learn the 50 chapters, and he also gave some special attention, special time to those chapters in which I'm not confident. Ultimately, he also going to have some weaknesses, means some chapters in which he is also not confident on. And it is also a possibility that I might have covered all those chapters. What are his weaknesses? Possible? Yes. So the weakness of the second person will be taken care by the third person. The third person will again cover all the 50 chapters, but he will give some more attention to the chapters in which second one is not confident on. And this chain will keep on going. Right? This chain will keep on going. Exactly, exactly. The individual algorithm is going to have some strong points and some errors also. So errors of one algorithm is going to be resolved by some other algorithm. And the other algorithm is again going to have some own errors. That error are going to be resolved by the third algorithm, and this chain will keep on going. Make sense? Make sense? In the group presentation we divide the task before, because that is the example of bagging, not the boosting. In the bagging we divide the tasks. I'll take care of this, I'll take care of this, you'll take care of that, and so on. We divide the task. That is the bagging, right? But in boosting, I will cover everything. I will try to understand and learn everything, but I'll try my best. It's not like I will feel I already have some other people to learn, so I can be a little easy with the things. I will try my best to learn everything, but still apart from that, if I'm not having much confidence on fewer of the chapters, I'll pass those fewer chapters to some next person. Okay. Though I have learned, but I'm not very confident on these. So please take care of these chapters as well. So he'll also try its best to learn all the 50 chapters, but he will give more attention, more importance to those specific 50 chapters. Right? Right, right, right. Yes, guys, everyone. Make sense? The concept of boosting. And this way we can actually try to boost the accuracy of the algorithm. In short, like long story short, we can just phrase it like the error of algorithm 1 can be resolved by the algorithm 2, right? The error of algorithm 1 can be resolved by algorithm 2, and that's how we can increase the accuracy. Make sense? Yes, guys, make sense? Easy? Easy? Boosting? Perfect. Now, will it become overfitted model? There are chances, but again, we like it's going to be a decision tree. We build the decision tree only, but we can definitely take care of the overfitting by those parameters, the depth and other things. But before also we are doing the same. If one model is less, we are going with the other model. Uh, Before, you mean to say in bagging? Are they both use? Are they both used or any one at the same time? You are talking about bagging or boosting, right? You are talking about either bagging or boosting. Only once at a time. Either we go with the bagging or with the boosting concept, not both. Okay. But before also. Okay. Okay. So the other algorithm is not actually taking care of the errors of the previous model, right? The next model was not actually taking care of the errors of the previous model. The next model is taking the entire. The new model has no knowledge of the previous model, right? We built support vector machines. Before that, we built KNN, but support vector machines have zero knowledge of what KNN does and what was the capabilities of KNN also, right? Yes, right? Yesterday we built different models, different algorithms, but then whatever, like if we created support vector machines, so support vector machines have zero knowledge about what KNN was doing, why KNN failed, and anything. There is no interaction between KNN and SVMs. It's basically us who are trying to explore the different algorithms and their accuracies, right? No, in bagging, we divide the entire data into different subsamples and we train let's keep the decision tree here only. Okay. In bagging, we will divide the entire data into different small subsamples and we will train different decision trees to every subsample, right? In boosting, we are not dividing the data at all. We gave the entire data to the first decision tree. First decision tree was not able to classify some of the observation. So those like for the second decision tree, we will again give the entire data. But the second decision tree will give more importance to those observations that were not classified in the first decision tree. And then there will be a third decision tree that will again try to classify all the observations, all the data, but it will give more importance to those observations that are the errors of the second decision tree, and this chain will keep on going, right? But at the end of the goal is to increase accuracy. What is point to know the previous model's error? In bagging, okay. Do we understood that example of appearing for a given exam? Yes. So now what's the point of telling the next person that I am not confident on these chapters? Yes. Yes, guys. What's the point of telling second person that I'm not confident on these specific chapters? These chapters were my errors, and the second person will try to resolve my errors. Yes. Yes, yes, exactly. That's what we are trying to discuss right now. The bagging and the boosting. In bagging, we divided the data and we trained different models, different decision trees. In boosting, we trained first decision tree on the entire data, but the first decision tree was not able to explain everything. So what the first decision tree was not able to explain, second decision tree will take care of those specific observations. It will give more attention, right? And this chain will keep on going. Understood? Yes, guys. Clear, everyone? What is the bagging and what is the boosting? Awesome. Now let's talk about their mathematics. Okay. Now bagging is clear. In bagging there is no such fancy equations or so. But in boosting there are some of such equations or such things. You can re-download. Yes, you can re-download. I have upgraded the file. You can simply re-download it. So let's talk about the boosting. So in boosting, the very first algorithm is ADA boost. Adaptive boosting, right? So adaptive boosting is the concept of giving more importance or something, right? Adaptive boosting is giving the concept of giving more importance. That's the same thing what we discussed. So suppose the total number of observation n is 700 here, right? Suppose the total number of observation n is 700. For example, we have the data set to classify and we have 700 observations for training. Possible? Yes? We have 700 observations and we need to build a classifier on them, right? We have 700 rows to classify. Okay, so we will give 700 values with same importance. I would say weights. Every value will be given same importance for the first decision tree, so the weights will be 1 by 700, right? And we gave this to the model M1. That's the first decision tree. Okay, make sense? We are trying to build the first model by giving the entire data set and every observation is having the same importance, right? So the machine learning model will try to classify all of them with same importance. There will be nothing like this specific observation is giving more, importance or something. Everyone will be treated fairly, and the first model is trying to classify all the 700 observations with the equal importance. Make sense? Yes, guys. Is it clear? Everyone? Yes. Is it clear, everyone? We have 700 observations. We are trying to build the model 1 first model and we are giving 700 observation to train the first model. Every observation will be given same importance, so that's why we have created the weights 1 by 700 for all the observations, right? So every observation is having same importance. The importance for every observation is 1 by 700 and it will try to learn. Okay? Correct? Perfect. Clear, guys? This is clear, everyone? Yes, will it be divided? I'm sorry, what needs to be divided? Yes, what needs to be divided here? Sorry. Okay, no problem. Perfect. So we gave 700 observations to the first model with same importance for all the data set. Now this will learn, and we have the learn trained model. We have trained model, right? Now, this trained model has its capabilities. Let's say on this trained model, if we test this model on the same 700 data, it is capable enough to classify 490 observations to the right class. But let's suppose 210 observations are not being correctly classified from this learning. Now these numbers are hypothetically taken, so like we are not picking these number as a calculated one. Let's suppose out of 700, the model was capable enough to classify 490 observations correctly. These observations are correctly being classified. But again, there are some observations that are not being classified that accurately, means 210 observations from 700 class are not being predicted to the right class, right? 210 observations from 700 observations are not being predicted to their respective class. They are being predicted to some another class, means they are misclassifications, right? These are the misclassifications. Make sense? These are the misclassifications. Okay? Possible? And these are the correct classifications. These are the correct classifications. Yes? Understood? Everyone? Okay, now this entire 700 data will be given to M2, right? Will be given to M2, but it will give more importance to 210 observations, 210 observation and 490 observation, right? So these 210 observations will be having more importance and 490 observations will be having less importance while training. Make sense? It is taking the entire data. It's only taking the 210 observation. It's taking the entire data. But those misclassifications will be given more importance here, right? The misclassifications will be given more importance here. Make sense? Okay. Now we need to understand how do we assign these importances. Let's try to understand, guys, how do we assign these importances. Okay. Now I need to do some cheating from my notes. Okay, yeah, I got it. Yes. Yes. Perfect. So once we train a model and we know how many observations are correct and how many observations are incorrect, actually it's in hard copy and you won't be able to understand my handwriting. I'll share them, but it's quite difficult to understand my handwriting. I'll share them. I'll convert them into PDF. Yeah. Okay. Now, so this is the model one. We will calculate the total error for a given model. Okay. There is a total error concept. So we will try to calculate the total error for a given model. So TE stands for total error. TE stands for total error will be calculated as the number of error observations, the number of misclassification, right? The number of misclassifications divided by total observations. How many total observations were there? So in this case, it's going to be 210 by 700. That is the total error. That's, I think, 3 by 10. Yes. And that is 0.3. Okay. That's the total error for model M1. Yes. This is the total error for model M1. Okay. Awesome. The total error is clear, everyone? Great. Now, after we have the total, we have to manually create each model while coding? No. We don't need to do anything manually while coding. Everything can be done with the fit function. Okay? We have dot fit function. Genie for us. Just give what algorithm we want to implement. That function will do everything. Okay? Perfect. Now, we need to calculate the performance of the model by having the total error. So we calculate the performance of model M1, and how do we calculate it? 1 by 2 log base E 1 minus total error divided by total error. That's how we calculate the performance of the model M1. Okay? This is the formula to calculate the performance. So we can just place the values of total error and we can calculate the performance, whatever it will be calculated. Okay, so that's the formula. How do we calculate the performance? Clear? Clear? Okay, now after we have the performance, we calculate the new weights. So the new weights for misclassified observations will be old weights into, so misclassified observation needs to have more importance, e raised to the power performance. That's how it will calculate the weights for the new observations. And again, new weights for the correct classifications equals to weights into e raised to the power minus performance. Okay, so see, the misclassified observations are having more importance than classified observations, and after these they will get normalized. They will get normalized so that the sum of all the weights should be equals to 1. So after, like, from the performance, it will calculate the new weights for the misclassified observations and the correct observations, and it will normalize the weights such that the sum of all the weights should be equals to 1. Okay, so we calculated the performance. After the performance, we are calculating the new weights for the misclassified observation, and the formula to calculate the new weights for misclassified observation is weights, the old weights, into e raised to the power performance, and the new weights for correct observation is weights into e raised to the power minus performance, right? We calculate new weights for misclassified and correct observations. Then we will simply normalize these new weights such that the sum of all the weights should be equals to 1. Easy? Easy? That's how adaptive boosting will work. That's how adaptive boosting will work. Perfect, guys. Adaptive boosting is clear, everyone? We need to specify how many models we want to build. That is the only stopping criteria here. We need to specify how many models, M1, M2, M3, such models, how many models we need to build. That's going to be the stopping criteria. Okay. And by default, it's 200. If we want to change, we explore somewhat less than 200 and somewhat greater than. By default, the number of estimators it will create is 200 decision trees. We can change if it's not giving a good fit. We can definitely increase it to observe whether we are getting a good data set or not. Good, whether we are getting a good result or not. Perfect. After this M2, now M2 is again going to have its own errors, and M2 is again going to have its own errors and its own correct classifications, misclassifications and correct classifications. So those misclassified observations and correct observations will be given separate importances for M3. So what we have done in M2 from M1, we will do the same for M3 from M2. Yes, right? What we have done for model M2 from observing the model M1, the same thing we will do for model M3 by observing the model M2. Okay? Sounds good? And so on. Yes, and so on. Until It reaches the threshold of models. Easy, the adaptive boosting. Now this sounds a good approach to improve the accuracy. Yes guys, this sounds a good approach to improve the accuracy. Great. Great guys, great. Now, if this adaptive boosting is clear, we can move to the next model. Let me know if anyone have any questions anywhere about the adaptive boosting guys. Let me know if there are any questions, anything. Or we are good. No questions? Yes guys, no questions? Awesome. Means we get used to do these algorithms now. How 1 upon 700 is equally? Okay, so if you have 700 observations, right? And you want to distribute something equally to everyone. Let me take some small example. If you have, if you have, five people and you want to distribute something equally to every person, you will take 1 by 5 for everyone. Let's say I have an apple and I have 5 people with me, so I will divide that, like I will give 1 by 5 of that apple to everyone so that everyone will get equal amount of apple. Yes, clear? Clear? Awesome. Okay, anyone, anything else? Yes, guys, any other questions? Anyone? Perfect. Perfect. Okay, now the gradient boosting. That's very interesting. Gradient boosting. Okay, let's use Excel for this because I need a table and I can't draw a table. I can draw straight lines. What is this? Okay. Mm, I just need a blank cell. Perfect. Let's see. Now, gradient boosting. Okay, suppose let me take a target variable y, okay, and let's pick some numbers 0, 1, 1, 1, 0, 0, 1. Okay, possible. That's my target variable, actual target. Possible? Yes, guys, that's my actual y. I will simply write it actual y. Okay, that's the actual y. Suppose now we can simply give x comma y to our model m1, and model can make us predictions on y, or simple pred y, right? This model can simply predict y. Yes, guys? Yes, does this make sense? We have a model m1, we give x comma y to get trained on m1, and m1 can simply make some predictions pred y. Okay, and now pred y are definitely going to be somewhere close to the actual y, not completely close, but whatever it's whatever is the capabilities of m1, it will give us some close results. So let's use the pred y somewhere close to the actual y. Okay, so if it is 0, let's say it's at 0.3. Okay, it's 1, it's at 0.6, 0.7, 0.5, right? 0.4, 0.2, and 0.9. Possible? Possible? Let me add some errors also. So this was predicted as 0.1, okay, and this was predicted as 0.6, right? Right? Okay. The actual and the predicted y is what m1 is predicting, but let's assume that m1 is not very much accurate. Let's assume m1 is not very much accurate. Okay. Does accuracy of a model means predicting closer values or predicting right wrong values? Both. It will make right or wrong only when it will make the closer values, right? So remember the sigmoid of y and that logistic operation. Suppose the cost function is the sigmoid here. So it will be close to 0, then only we will consider it 0. If it will be close to 1, then only we will consider it 1, right? Make sense? Though there are a lot of other things that are into operation, but we are picking this specific case only to understand how the gradient boosting will work. Okay? This is basically to understand the approach of gradient boosting. Okay? Perfect. Clear? This predicted y and y is clear, everyone? Awesome. So now, once we have the predicted y, we can calculate the error that is we are getting from model M1. We can calculate error M1. Yes. Actual minus predicted value. Y minus pred y. Okay, now tell me what will be the error here. 0 minus 0.3. Here. So that's going to be error. That is going to be the error for the model M1, right? These will be the errors. Clear, everyone? Yes, guys? The error thing is also clear. Fourth one, 0, 1, 2, 3, 4. Oh, my bad. 0.9. Yeah. Clear? Okay. Now suppose we build a model M2, by giving x and error of m1, right? We are building model m2 to predict the error from m1. Possible? Now we don't want m2 to predict y, we want m2 to predict what was the error in m1. Make sense? Yes, guys? The second model is not predicting the target variable. Rather, the second model is predicting the error. Make sense? Why? But won't the accuracy be same for both the models? No, we'll understand that. We'll understand that. So, is this make sense that we can create another model that will predict what's going to be error for M1? Yes? Now, M2 will predict error M1, right? M2 will predict error M1 because we have trained M2 on error M1 itself, so it will make the predictions on error M1, right? Yes, makes sense. We have trained M2 to predict error M1, x comma error M1, so it will make the predictions on error M1. Is it clear? Perfect. So let's see the error M1, the predicted error M1, not error M1. We will see the predicted error from M1. Predicted error M1. Okay. Now we know the predictions are going to be close to these values. Predictions are going to be close to these values. Yes. Okay. Now let's see how we can make them more closer. So suppose our predictions are more, concentrated towards the 0. So if it is minus negative value, it's gonna be smaller than this, right? And again, if it's a positive value, it's gonna be smaller than this. So the predictions are, let's say, minus 0.2. Here it is 0. Let's take 2 itself. It is 0.1. This is 0.6. Let's say this is minus 0.2 again. This is minus 0.3. And let's say this is 0. Okay. Possible? These could be the predictions. Possible? Possible? Yes, guys? Perfect. Perfect. Now, from this, what will be the predicted y from M2 model? We will be calculating predicted y from model M2. That's going to be predicted y, pred y plus pred error M1. Yes? Predicted y plus error M1. We can do this? Okay. Now let's see what's spread y from M2. Yeah. Now sum up this value and this value. 0.3 minus 0.2, 0.1, 0.6, 0.2, 0.8, right? 71, 0.8, right? 0.7, 0.4 minus 0.2 minus 0.2, right? And 0.6 minus 0.3, 0.3. Okay, it should not be minus, my bad. So sorry. 0.2, yeah. And this is going to be 0.9. Okay, now we can see we are more close to the real values. Yes, guys, now we are more close to the real values. Yes, we are more close to the real values, the actual y. So that is how the gradient boosting is going to improve the accuracy. That is how the gradient boosting is going to improve the accuracy. Easy? It will stop iterating automatically. It will stop when there is nothing to predict in the error. There will be a state when there is nothing to predict in the error. But we need to have good amount of data and all variety of data for this. Definitely, we need to. The amount of data is there for every possible algorithm, not only for this. We predicted the errors and then rectified them. Exactly. Basically, we are building a second model based on the error and then adjust to get more accuracy. Yep. Based on the training itself, the same way we predict sales for the unseen data. Yes, the same way we predict the target variable for unseen data, right? Same way we will predict error for unseen data. Make sense? When we like in the big mart sales problem, we don't have the sales, but we predict the sales based on the factors, right? Similarly, we will predict the errors based on the training. Yes? Awesome. So here we are trying to build a model that will predict the target variable. Now that this model is going to have some errors, the second model will predict the error of the first model. And when we combine the first model's predictions with second model prediction, we will get more accurate predictions. Right? Exactly. Then definitely there will be some error in errors. And that error in error will be modified, will be trained by some other model. Let's suppose this predicted error has some error, but in spite of having that error, we are getting more closer to the target variable, right? Still, we again are going to have some error here, right? Here also there will be some error that belongs to model M2. We can calculate error for M2, right? Whatever will be the actual and predicted value, the difference between this, and we can build another model to predict this error. Yes, yes, got the logic? Easy, easy. Not all the time close to 100%, but this is the way we can improve the accuracy if a single model is not going to, is not helping us in more accurate predictions, right? If the single model is not actually helping us in accurate predictions, this approach is definitely going to increase the accuracy, guys, no? The number of iterations, by default, it will stop. There are two rules. We specify the number of models, but it can also stop once it has nothing to predict in the error. Once there is no variance left in explaining, left to explain in errors, that's the criteria where it can stop. Otherwise, the number of models we have given, uh, they, no, it went out for the number of models. It completed the number of models, right? Now, in this case, the models are going to be the decision tree based models, right? They are going to be the tree based models, but we have a lot more variations in the tree based model. We can create, I'll show you when we use gradient boosting, this gradient boosting or extreme gradient boosting, we can actually play with the cost function, the function to build a decision tree, right? The entropy could be a possible functions, the Gini, binary, logistic, and there are different functions to create a tree. So we can actually play with different types of functions while creating the tree here. Can we give X and predicted error from? No, we cannot. In that case, we will lose M1 and we won't be able to get the predictions predicted Y itself, right? In that case, we will lose M1 and we won't be able to get predicted Y for the unseen data. If we have overwritten the model M1 with the errors, so first at the very first iteration, it will only predict the errors. But we actually need the target predictions before we make the predictions on errors, right? Right? Perfect. Understood, guys? Understood, everyone? Awesome. So now bagging and boosting concept. Both are clear? Clear? Interesting? Awesome. So this is gradient boosting. Extreme gradient boosting also works on the gradient boosting concept only. It's extreme because it's quite faster and optimized. Yes. Extreme gradient boosting or XGBoost is a third-party library built over C. I think it's, yeah, built over C or C++. That is more optimized. That has more, advanced optimization features like parallelization, distributed computing, cache optimization, continuous training. So it's more optimized and it has a lot more, distributions for the data. Ideally, there are two concepts. This form of gradient boosting, extreme gradient boosting also works on the same principle. It is more faster in execution. It's this XGBoost library is built over C++ languages, right? When we install XGBoost in Anaconda or in pip, it also installs some dynamic link libraries in our system because they are not built corely on Python itself. They are built on C++. So there are dynamic link libraries through which we can interact the Python with C++. Correct. So extreme gradient boosting, XGBoost is not actually different from gradient boost. It works on the same principle. It just has more advanced feature like parallel computing, cache optimization, and much more. Okay. Yes, great. All good, everyone? Perfect. Let's continue with the code and let's finish that horses one case study and let's do one more case study today. Okay, let's finish the horses and let's do one more. Perfect. So that's how we create a random forest classifier. Random forest classifier, just importing random forest classifier. Then creating an object of random forest classifier dot fit function that will train, that will do the magic. It will train and create the forest, and we can simply calculate the scores. Again, overfitted model, right? Again, overfitted model. Yeah. So now we can again go for the hyperparameter tuning. Apart from max depth and minimum sample leaf node, we have number of estimators. How many decision trees we want to build for a random forest? Also as a parameter, right? So the n estimator is the number of decision trees we want to build for a random forest. Okay. So let's try to do the hyperparameter tuning and let's see whether we get some increase in accuracy or not. Best parameters, okay, it's still fitting. It's gonna take time. 160 trains, 180 fits, 60 candidates. Let's wait until this finishes, and it will give the best score and best parameter. Okay, so we understood what are these values. What why we are giving 150, 200, and 250 because 200 is something default, right? 200 is something default value. So let's explore something lesser than 200, something greater than 200. And by the first fit itself, we will get to know that whether we need to increase it more or we need to decrease it more, right? It's taking time. Grid search we always use on complete data. It's not X-test. No, because grid search does the train test split by itself, right? Grid search does the train test split by itself. Now, how would we know if it's using bagging on boosting? What actually you are referring by it here? The grid search or what? Yes, random forest. Okay. Yes, right. Random forest was what type of algorithm? Anyone wants to address this? Random forest was what type of algorithm? It was bagging. Correct? How do we know whether it's using bagging or boosting? Awesome. Now let's proceed and let's see what it used. Number of estimators, it decreased, and let's see what's the best score. 70%. Improved a bit, right? Now we can again reduce the estimators more to check, but I won't be doing it right now because it takes time for the execution. But yes, now we got the idea. We can play with these numbers to see whether we are improving, whether it's getting some better accuracy or not, right? Clear, guys? Yes. Feature importances, random forest will also tell us the feature importances. We can plot the feature importance like this. The same way we did in decision trees. So that's also we can do on random forest. Clear, everyone? Yes, guys? Perfect. Any questions about this, or we are good? You can see the boosting now. Great. Let's proceed to the next algorithm, that is adaptive boosting. Okay. So same way, we have created an instance variable, we have created an object, we have invoked .fit function, the magic function. It will train the model, and that, adaptive boosting, whatever we discussed, calculation of weights and everything is done. We simply did .fit and it's done. Boom. Model dot score will give the test score. Okay, brilliant test score, 83%. But okay, this is the train score and this is the test score. Test score is not that good, right? So let's try to play with the number of parameters, number of estimators, and let's see whether it's giving some good accuracy or not. Okay, now again, it's not very necessary to get better results and boosting algorithms, because we have observed in this data set, it's not the algorithm, it's the data set that's not giving the good accuracy, right? Yes. In this specific case, it's not because of the algorithm, it's because of the data set is not balanced. We cannot get that good accuracy, right? Okay, so random forest still gave some better accuracy, around 70%, but adaptive boosting is not giving any satisfactory results. Model dot score. If we need to do model dot score again, we need to train that model first, right? We okay, you are talking about this. So in that case, we need to train that model again on a best parameter. Let me show you how the way we did in, I think we did it in support vector classifiers. See here, this was the best score from Grid Search CV. Yes, this is the best score from Grid Search CV. Yeah, I have already updated this drive. Now, we again created the classifier and we have specified the best parameter, 10 and this, whatever it was. We trained and now it is giving that good accuracy. Yes. Earlier, CLF.score was giving 57%. But now, after retraining with the good parameters, it is giving the best accuracy, best score. Make sense? Yes. Retrain the algorithm with the new parameter values. Right? Okay, perfect. Let me just go back to place where we were. Okay, random forest we have done. And we have also done ensemble learning, adaptive boosting. Okay, so there is also a cross validation method called k-fold cross validation, right? There is also a cross validation method called k-fold cross validation. That is just, okay, we know what Grid Search CV does. It will do multiple train test split and it will retrain it again and again for different values of parameter, right? We know the concept of Grid Search CV. Everyone, we know the Grid Search will do the train test split multiple number of times with respect to the CV we specify, and it will, check every possible parameters and give the best accuracy. Okay, now just exclude the parameter thing. Just exclude the parameter thing and only the cross validation approach. Splitting multiple times, checking multiple test accuracy. That's what k-fold cross validation does. The k-fold cross validation will simply do multiple train test splits and give multiple test accuracies. It will, like, from the grid search CV, there will not be any any involvement of the parameters testing. Only it will take the x and y, the input data and the target data. Instead of CV, we specify the number of splits. So if it is 5, the test size is going to be 1 by 5. Oops. The test size is going to be 1 by 5, that's 0.2, right? And it will do train test split five times with test size 0.2, right? Without any parameter or something. That's what the k-fold cross validation does. Correct? Yes, guys? Correct? Sure. So remember the grid search CV? Remember the grid search CV? Okay. It takes care of the parameters also. Params, and also does the cross validation, right? Just remove the parameters part and just include the cross validation. That's the k-fold cross validation. Okay. Anything can be used. See, the grid search CV can be only used when we need to tune the parameters. But in k-fold cross validation, there is nothing like parameters. So if there is a requirement to work on the parameters part, we can't use k-fold cross validation in that case, right? That's the condition. Okay. Clear, guys? Everyone? The k-fold cross validation, how exactly this is working? We simply created a k-fold object by specifying the splits, and shuffle equals to true is simply shuffle the data before making the split. It will simply shuffle the data before making the further split. Now we have created the adaptive boosting classifier with 400 parameters, what we have discussed here, 400 estimators. Now model selection dot cross validation score, specified the model, the data, and the cross validation should be k-fold. Okay, easy. So this will give us, so it's 5, it will give us 5 accuracy and the average of the accuracies. It will give the 5 accuracy and also the average of accuracies. Easy? Yeah. So the average accuracy is 63% and these are the average accuracies. Now see, this was the case we were talking about. There could be a possibility in different train test splits. Somewhere we are getting very good results, that is 71%. Somewhere we are not getting that good results, that is 56%. Right? Right? So if we only do one train test split, we may get a biased accuracy. Possible? Suppose there are few observations, few 2-3 observations that are not very suitable for the data. They are causing a huge error. So if those observations are present in training, we are going to get good testing accuracy. If those 2 observations are present in testing, we are going to get bad testing accuracy, right? And this can give a biased results. On an average, we can say our model is giving 63% accuracy, right? Got the concept of k-fold cross validation, why this is important? And I think there was some question similar to this problem also, right? When we were getting different accuracies on different executions. So this way we can get resolved. This way we can get that thing resolved. Correct? Easy, interesting, everyone? Can get search CV give accuracies for different CVs. Just a sec. If we check the best score, it gives the best score. Let me just check what is the oops. What is the parameter to get all the accuracies? Score. It will give the score based on the data set. What else can be used? And jobs, get params, error score, best score, best params. No, it's going to give the best score only. Best score. Let's see CV results have something. Yes, yes, yes. Actually, it has the score. What was the grid search? Have we done the grid search on ADA Boost? We have done the grid search on ADA Boost, right? Okay. There were 9 fits. And so it must be telling 9 accuracies. At times, split 0, 3 accuracies, split 1, 3 accuracies, split 2, 3 accuracies on 3 values of n splits. Okay. So this way we can get the all scores, CV results. Yeah. Split 0 test scores. This is for 200, 400, 500. What all parameters we have given? 300, 400, and 500. So this was the accuracy for 300 estimators, 400 estimators, 500 estimators. Second split 300, 400, 500. Third split 300, 400, 500. Okay. Awesome. Perfect, guys. All good with the classification algorithms. Now we can also build the XGBoost XGB classifier the same way. We can simply create a XGB classifier the same way and we can check what's the accuracy. Interesting? Yes, guys? Easy, everyone? Clear? Easy? Now, it can be used for the continuous variables also. The way we have XGB classifier, we can use XGB regressor, right? So, from XGBoost, okay, let me just show you what all we can do. All the classifier we have used, we can use regressor instead of classifiers also. XGBoost dir XGBoost. XGB regressor, right? And XGB classifier. Similarly, if I show you the other one where we have imported the ADA boost, sklearn from Ensemble. ADA boost classifier, ADA boost regressor, right? So all regressor classifiers we have, we also have the regressors for them. Okay. I have shared the file. I think it was in day 9. Yes. In day 9 itself, inside the classification, I have updated the same file, algorithms classification algorithms.py. Okay. Sure, guys. Now we can take a break. Let me start the polls. And after the break, we will do one more small binary classification problem for logistic, right? Remember the logistic regression? We haven't implemented the logistic regression here because it was not binary classification problem. So let's do one more small classification problem on logistic. And yes, that will be the end for the classifications. Okay, cool. We can, the polls are open, guys. Yeah, let's get back after 20 minutes, guys. Hey everyone. So everyone is back now. Perfect, guys. Let's start and the next thing is we have already downloaded that folder. So now we need to open Titanic case study. Where is the class assisted practice classification? No, that's not there. Okay, that is there in linear algos because that is the classification case study. Let me upload it in day 10 and you can download from there. Yeah. So I have uploaded some code files and some data sets in day 10 folder. Download all of them, guys. Download everything from day 10 folder. Download everything from the day 10 folder, guys. The server controller, please try again later. What later? Everything is uploaded. Yeah, done. And we need to open this assisted tightening folder. Assisted tightening file. Perfect. Not a big case study. We can quickly do it. Okay, so this is a shipwreck data set. We all are aware of the Titanic tragedy, right? Yes. Yeah. DiCaprio. We all are aware of this tragedy also and also the movie. Okay, now the target is going to predict whether a passenger is going to survive or not. The target is to predict whether a given passenger is going to survive or not. Make sense? Make sense? Great. Now let's quickly import the libraries and see the dataset. Yes or no means logistic regression. Yes, it's a binary class classification. So we can try logistic here. Binary class classification, so we can try logistic here. Great. Now it's not we can only try logistic, definitely we can try other algorithms also. But the case study on the horse, we cannot use logistic because it was actually three class classification, right? Sure. So we are importing these libraries and I believe we all are aware of all these libraries here, guys. Yes? Great. Let's read the train.csv file. Oh, sorry. Yeah. Let's read the train.csv file and let's understand the dataset. We have 891 observations with 12 columns. And if you see the dataset, that's how the column looks like. We have passenger ID survived. That's going to be our target variable. Passenger class, in which passenger class the patient is, sorry, the passenger is, the name of the passenger, age of the passenger, sex of the passenger, age, sibling or spouse, means any sibling or spouse was also boarded with that passenger or not, right? This is sibling or spouse, right? And this is any parent or children was available or not, right? Right? Uh, there be different columns for, sorry. So either sibling or spouse, anyone from the same generation is available. Parent, children, anyone from other generation is available. Okay. Now we have ticket ID, the fare of the ticket, cabin, and embark. Embark date, from which port the passenger have boarded the ship. That's the embarked, right? From which port the passenger have boarded the ship. That's the embarked. Clear? Perfect. So now what are columns we can drop? We can drop the name, we can drop the ticket. So as of now, we can only see two columns that we can drop, right? The names and the column, the name and the ticket column. These two columns, yes, passenger ID also. So we can drop these three columns because they are not going to be helpful. Fair, let's keep it. It could give some meaningful insight also. Let's keep the fair. Like that, like we cannot just say like by just observing the data set because fair is a numeric column, right? And statistically, it can give some significance, right? We'll talk about cabin and all. We'll talk about that. But as of now, if we see the discrete ones, we can drop these three values, right? Great. Perfect. Let's proceed and let's work around data set. So let's see the survived. We have 342 observations, 342 passengers who survived and 549 passengers who didn't survive. The males and females, less females and more males, and embarked. So that's the just data observation. How many observations? What is the proportion of the data classes? Right. This is the actual data. Actual data, you mean to say from that real Titanic case, real Titanic tragedy? Not sure if it is really from there or that's just a research practice. Oh, so that's a case, that's a specific practice case. We can't be very sure it's actually, it is actual from the Titanic passengers or not. Perfect. Now, let's see the missing values. Three columns have missing values: age, cabin, and embarked. And if we check the percentage of data missing, here it is. Okay, now tell me what we should use in what column, guys? Yes.